Good evening, folks. Well, today I had a rather interesting time listening to Ranty Flat Earth's show while driving to work. And I found it astonishing. Astonishing why? At the level of ignorance about Snell's law and how light bends. Also, I've noticed lately that flat earthers are going overboard with a film that they've been watching and they name it Black Swan. So apart from the fact that they misuse the Black Swan analogy, they have this completely wrong. In other words, what they assuming is that the one time that they think they see something that shouldn't be apparent on a sphere means 2,000 years of science, all the rockets in space, all the satellites, all the science, Kepler, Newton, are all nonsense. That is their view. So the one time that they notice that, hang on a second, this really looks like it should be on a flat earth, all of a sudden they think, wow, all of science has been debunked. Because if you say there are no black swans and you spot one, well, that means that you must be wrong. That's not how science works. So, let's swing this over and we'll start with some basics about why light bends. Okay, and how it does. What we'll do after that is go into more detail. So we'll look at the specifics that relate to the oil rigs, which are the focus of this particular video. So let's get on with it and let's cook that black swan. Okay, here we are back again. So now you can see on my whiteboard here, I've got Snell's law, and we're going to be looking at refraction. Okay, and this pretty much for the layperson means the bending of light. Now let's have a look at some things first over here. So in this diagram over here, we've got two media. We've got water with a refractive index of 1.33, and we've got dry air with a refractive index of 1.0003. So pretty much close to 1. A vacuum would be a solid 1. So this is dry air, would be not that far off from the refractive index of a vacuum. Water is a long way off. Now, this here is the normal. Normal meaning perpendicular to the media that you're looking at. Okay, so this one here is the ray of incidence. So the incidence ray. This one here is the refracted ray. This particular one over here. This here is the incidence angle, and this here, theta 2, is the refracted angle. So as you can see, the rays that coming in, it bends because this medium is more dense. The ray bends, and apparently to the observer up here, the observer thinks that they're looking at a straight line. However, they are not. They're actually looking at this particular ray. This is the actual ray. This is the apparent ray. This is the actual ray that's coming through. So let's say there's two fish over here. The observer thinks that the fish is over here. This red one. That's what the observer thinks. Whereas in fact, the fish is over here. So good fishermen with their harpoons know better than to throw the harpoon where they think the fish actually is. They will throw the fish understanding that there's a angle of refraction, and they'll throw the arrow so that it gets the fish. So anybody who's ever done that kind of fishing with a harpoon knows this. Okay, let's have a look across here. Here we have dry air around 30%, so that's 30% humidity. It's pretty dry. And then here we've got 65%, getting a bit more moist. And then here we've got 80%, much more moisture. Again, what's happening is the refractive index is changing. So over here 1.0003 as it was over here for dry air, and then 1.1 at 65% and 1.3 at 80% and more. In fact, that can go all the way to 1.32, 1.33, pretty much what water is. So, as you can see, it will bend. So it bends first in the dry air, bends a bit in the moist air at 65, and bends even more at 80%. So while there is a gradient, the light will bend. It will bend more and more through the gradient. As it gets more and more dense towards the water, the ray will bend more and more. If you have a look over here, we've got the ray going through various layers, and as it's going through, it's bending. And as you can see, we've got an object over here. This object is loomed. It's loomed, and it's loomed up here so that apparently it looks as though the observer thinks that they're looking in a straight line, whereas in fact they're not. They're looking over here. This is the actual ray that's going between their eyes and this object. To them it appears as though the ray is actually going from here to here. That's called looming. If they took a gun and shot it at this thing over here, they wouldn't get it. It's a bit like the fisherman trying to get this one. It looks as though it's over there, but it isn't. It's down here. It's the light that's bending, that's causing it to look as though it's up here. No matter how Ruhiv tried to explain that, these two people just couldn't get it. It was simply astonishing. Now, you might ask yourself, how is it that light gets to bend? Well, light does act as both a wave and a particle. It's got properties of both. Now, I intend to do a video soon which actually goes into the physics of light, so that we can have a look at that in more detail. However, we'll just proceed with the idea that light does travel in waves, and a wave front approaching through one media at an angle approaches through one media at an angle, then when it reaches this particular different density, will then bend, just like it did over here. It bends. So the wave front changes. It changes the wavelength over here. The velocity changes. So here, the wave comes down to this medium and then changes. Lambda is x, for instance, and lambda nx over here. Now let's just talk about this for a minute, because I haven't mentioned Snell's law in terms of refractive index and angle. So here's the angle, theta 1, theta 2. Over here, if we had the normal through here, that would be theta 1, theta 2, and so on. So N1, which is refractive index 1, the sine of the angle 1 is equal to N2, the refractive index of the next media, multiplied by the sine of the angle of refraction of that one. So you've got angle of incidence, angle of refraction. You can change this formula around and you'll notice that it's proportional. So N1, refractive index of the incident ray, over refractive index of the refracted ray, N2, is equal to sine of the angle of the refractive ray over sine of the angle of the incident ray. Now this happens all the time. This is entirely predictable. So when the calculators make up the distances and the amount of looming and other light phenomenon that relates to refraction, they take this into account. Okay. All right. That was rather simplistic. I hope that you managed to get something out of that and got just enough so that we can now proceed to the next part of this, which will be how that image that they call this black swan gotcha image actually works. So what I'll do now is I'll finish off this video. If you like what I've said, please press the like button, press the subscribe button, do both, or press the dislike button if you don't like it. Go ahead, do it now, I'll wait. Thank you, good. All right, now, and then I'll see you in the next video where we'll actually have a look at this black swan nonsense and see if we can't cook that goose. Cheers. See you next time.